Welcome back to Honors Calculus. In this video, we're going to look at what I think is the single most important application of calculus, and that's really saying something. It's also one that really often gets overlooked, and it's a real shame. The idea here is called propagation of error. The idea behind it is that every time you make a measurement, you are introducing some error into the situation. Not because you're making mistakes, but because measurement is inherently flawed. Right? That's an idea that's technically science, not math, but I think it's very important to stress before we go into this. When I'm talking about error, what I'm talking about is that the instrumentation that we use to measure things is inherently flawed, and it is impossible to get exactly the measurement of an object. If you grab out a ruler that is marked to the nearest 64th of an inch, and you try to measure the length of a steel rod, you are inherently stuck to within 1/64th of an inch of the correct response, because that's all the better your ruler actually is. If you grab out a vernier scale calipers that is marked to the nearest 10th of a millimeter, and you try to measure the width of a six-sided die, you are inherently stuck at a result that is to within a 10th of a millimeter of the correct result, because that's all the better your instrument is. So let's imagine a relatively small cube, and we're using a vernier scale calipers to measure the length, the width, and the height of the cube. Each of our measurements has a tolerance of nearest 10th of a millimeter. And using the length, the width, and the height of the cube, our plan is to calculate the volume of the cube. Based on what we just did, what tolerance does our result have? That's the question that I want to answer in this video. But before we do that, we're going to have to look at a different mathematical construction of implicit differentiation that we've talked about before. That other construction is known as differential form. There is an easy way and a hard way to understand differential form. I wish that I had enough time to make the hard way make sense. So I'm going to stick with the easy way. We've been writing derivatives in a couple of different forms. F prime of x, dy over dx. And I stressed when I first wrote it down that dy over dx is not a fraction. It kind of looks like a fraction, but it's not a fraction. I'm going to completely ignore that advice. Pretend that dy over dx is a fraction and multiply both sides of the equation by dx. I get that f prime of x dx is equal to dy. This is called the differential form of the derivative. Again, there are a lot of subtle things that are happening here, some of which we'll be addressing a little bit more later on in the course, but for right now, just accepting that it's a thing that we can do. Again, you can't do this in general. You have to have certain conditions to be true about the derivative f, or the function f and the derivative f prime that I'm not going to get into right now. We'll get into some of them a little bit later in the course. When I'm differentiating implicitly, I can think about things this way as well. So for example, if I have something relatively simple, consider 2x squared plus 3y squared equals 5. I'm going to call my operator now just capital D to say that I'm taking a derivative, and I'm going to write it in differential form. The idea here is that I'm no longer making a claim whether I'm differentiating with respect to x or differentiating with respect to y. And so I have to use the chain rule on every variable. When I differentiate 2x squared, I will get 4x. But to think about that and to write it like that, I had to take a derivative with respect to x. So to denote that that's what I did, I multiply times dx. When I take the derivative of 3y squared, I get 6y. But in order to think about it like that, I have to be thinking about differentiating with respect to y. And to denote that, I write down dy. On the right-hand side, the derivative of 5 is 0. I could rearrange, I could solve for dy over dx, and I would get the exact same y prime that I got differentiating implicitly previously. It works. It's more trouble than it's worth, but it works. So I don't want to go into that one in further depth. Instead, I want to look at that example that I was talking about at the beginning. Let's consider a box. And let's do our best to draw something that actually looks like a box and not like something crazy. And just generically speaking, the edges of the box can be labeled as the length, the width, and the height, L, W, and H. And here is practically why differential form is going to be important to us. When I'm thinking about V equals LWH, L, W, and H are not changing. They're not changing with respect to time. They're not changing with respect to orientation. But I still want to think about the differential, the change between my exact value and the value that I measure. So I want to think about that as the derivative. I don't have anything to take a derivative with respect to. So if I think about a slight change in the length, a slight change between my measured value and the actual exact value, which I can never know because I never can have a measuring tool that measures anything exactly. Every measuring tool has some tolerance. So DL, DW, and DH are the tolerances of the measurement of each of those things. In this example, all of my tolerances are going to be the same because I'm going to assume that I'm measuring everything with the same thing, vernier calipers in this particular example, but anything that you might have on hand. And then when I use those measurements, I will calculate my volume V. I will get some answer. And there will be a tolerance to the calculated value. I'm calling that tolerance dV. If I differentiate implicitly, the differential of V is dV, and then I have length times width times height. It's the product of three parameters. So I need to use the product rule to take the derivative. The derivative of the first times the others is going to be dl times w times h, but we generally write it with the differential at the end. So I'm going to write it as w times h times dl. Then we'll have the derivative of the second one times everything else. Again, I'm going to put the differential at the end, so it'll be L times H times dW, and then L times W times dH. So if I measure this cube, if I measure this box, I get out my calipers, and I get that the length is 35.2 plus or minus 0.1 millimeters. The width is 47.6 plus or minus 0.1 millimeters, and the height is 27.9 plus or minus 0.1 millimeters. Again, plus or minus 0.1 is me marking down that the calipers I'm using are marked to the nearest tenth of a millimeter. That's all the more detail I can get out of these. That is the tolerance of the measurement. And because I'm using the same tool to measure length, width, and height, the tolerance of all of those are the same. That doesn't always have to be the case. But with that information, I can calculate that the volume of this thing is the length times the width times the height. So that's 35.2 times 47.6 times 27.9. Grab out my calculator. And I get that the volume of this thing is 46,747.008 is what my calculator spits out. And it looks like that is exact. All right, so that's what my calculator spits out. And what I noticed right away is 0.008. That's measured to the nearest thousandth of a cubic millimeter. And it seems to me that that's probably being more precise than I really deserve to be. And that's where the differential comes in. I can calculate dV, which is going to be my width, 47.6, times my height, 27.9, times dl, the tolerance in L, which was 0.1. And then I'll have 35.2 times 27.9 times 0.1, and I will have 35.2 times 47.6 times 0.1. And I can throw all of that into my calculator as well. Right? And calculating that, I get that the tolerance on my measured volume, on my calculated volume, is 397.727 cubic millimeters. Which means that if I want to report this volume with its tolerance, I'm saying that the volume of this thing is 747.008 plus or minus 397.727 cubic millimeters. And I think that that immediately illustrates why having all of these digits is kind of silly and not really valid. And so what to do from here will change depending on what kind of application you are looking at. And in fact, in a lot of applications, even thinking about this much detail is more than you need, but it is something we can do. So there are applications where it's worthwhile. What I generally do is I will look at my tolerance and I will round it to its first digit. In this case, its first digit is a 3. The next digit is a 9, which says round up. So I'm going to write my tolerance rounded up to 400. Right? I rounded that in the nearest 100. So then I go to my volume and I choose the exact same spot. And I say, I'm going to round this to the nearest 100 as well. $46,700, right? The next digit is 4, which says round down, right? And that is a clearer indication of what's happening. Is it exactly the same range? No, it's not. But we generally can assume fairly safely that the absolute extremes of this range are not something that we hit because our tolerances are random. Some of them are going to be above, some of them are going to be low, and on the balance, it's going to be somewhere closer to the middle. So the fact that we're losing a little bit there is not that big of a deal. If you really needed that, you could look to statistics for some more information. But this gives us a pretty nice rule of thumb. Like I said, there's an easier rule of thumb that you might come across called accuracy and precision. The number of significant digits in a number can be used to try to figure out where to round. This is a little bit more exact than that method. If you need even more exact, there are statistical tools that you can use, but this is the one that is based on calculus, so that's the one that I wanted to talk about here. All right, let me get my head back out of the way, and let's look at a similar problem here for you to take a little bit of a look at. And in this case, I want to look at the rate law. Distance is velocity times time. So distance equals velocity times time. If your velocity is 55 plus or minus 5 miles per hour, which is about the accuracy and precision you can get from a speedometer on a car going down the highway, and your time is 3.5 plus or minus 0.3 hours. 0.3 hours is about 15 minutes, somewhere between 15 and 20 minutes. Using those, I want you to calculate the distance that has been traveled, which is a simple algebra problem, and more importantly, the tolerance on the distance that has been traveled. How much error is possible in that measurement or in that calculation given the errors that we know are possible in the measurements. This is a really annoying problem because we're going to be talking about d, the distance, and d, the differential, but I'm confident that you can get through it. Take a few minutes, see what you get there. I'll see you in the next video.